Do you notice anything different about me? Do you notice bags under my eyes? Maybe my hair is messed up. I'm slouched over because my back hurts. The reason for this, level friends, is that I'm tired. The reason that I'm tired is another Linux local privesc has dropped, and again, much like copyfail, its predecessor, this one affects universal versions, every version of Linux, and it's out right now. And I don't think there's a patch for one of the variants. We're in a weird spot where people, probably through AI, are getting very good at finding vulnerabilities. In this video, we're going to talk about how Dirty Frag works and why we're probably going to see a lot more of these bugs coming out in the near future. Now, if you're not aware, copyfail kind of set off this fire, right? This weird kind of bug primitive where effectively through the use of the splice operator, you're able to take a file descriptor, like a socket that's doing something weird, and then attaching another file descriptor for a page or a program that you don't necessarily own. Think user bin su, think Etsy password, right? This ability for you, the user, to put the page of memory into kernel memory that you don't control, but have the kernel do things on your behalf. And so copyfail did just that. Copyfail spliced together a socket that was doing a particular kind of operation in the crypto subsystem that allowed you to do a 4-byte out of bounds write into that page, giving you the ability to overwrite a page cache entry for su and giving you control over the su program. Now, this was talked about and everyone freaked out and patched it, and this probably for most people went away, sort of. But then I think literally yesterday, this little doohickey dropped, right? We're talking about Dirty Frag. So Dirty Frag is kind of the follow-up to copyfail, where we're seeing another vulnerability that's a la copyfail, but a different bug. Dirty Frag is a vulnerability where the same pattern is reproduced on top of the frag of a nonlinear SKB that originated from the splice. So I know that's a lot of words, right? I'm gonna try to break down what that means, okay? So the same pattern reproduced on top of the frag of a nonlinear SKB. Okay, so here's generally what's going on when they say all of those scary letters together. So when you have a socket, right? This is literally just a socket. The socket itself is just a file. Inside of the kernel, there's a variety of other structures that represent the socket and the associated data, okay? When you receive data from a socket, that data lives inside of an SKB. The SKB is like a socket buffer, okay? It is the data that represents sockets. Now, when we have an SKB in the kernel, there are two kinds of SKBs. There is a linear SKB, which means that all of the data exists in a single page. We have one page of data, okay? Now, if it's not linear, meaning a lot of data was put into the kernel, this means that the page is really, or the data is really large, it represents multiple pages. This is referred to as a non-linear SKB, okay? Which means instead of a single page, we have these things called frags, right? This is similar to, in my previous video, we talked about scatter lists, right? Where a non-linear SKB is literally just a array of page, offset, and length triples, right? And it's an array of these that represents the different pages, the offsets into them, and the lengths that make up the chain of data, right? So again, my example is if I put 40,000 A's into a socket, right? That cannot be contained in a single page of memory. So the kernel will use a nonlinear socket buffer to represent that data. The problem that gets into place here, similar to copyfail, is if the user does a splice, which means you take a pipe and you basically join together one file descriptor and another, which creates a splice operation, you're able to arbitrarily append data to the fragments of that socket buffer. So for example, if I were to do the splice operation, right? If I were to do the splice of my socket file descriptor and the file descriptor 2 that points to Etsy password, for example, what's happening is in the kernel, there's a structure now that represents pages and offsets that represent the data from my file descriptor, as well as the data from the Etsy password pages. And again, these are all page cache entries, which means that other programs that reference that page later in memory are going to use this entry. So if an out of bounds write occurs anywhere during this process, the contents as seen by the kernel of Etsy password changes in memory, which is not good. And so what's crazy about Dirty Frag is that Dirty Frag is actually two separate vulnerabilities. Like, this is being marketed, I guess, as like one vulnerability, like, oh, the Dirty Frag. No, Dirty Frag is literally two different bugs. The reason they chained these two together is that to run the ESP page cache write vulnerability, you need to have the ability to make namespaces in Ubuntu, which may not be allowed by various app armor configurations, kind of like the SE Linux, I guess you will, of Ubuntu. And so to make sure that this is truly universal, they just kind of tossed in another vulnerability, which is the same primitive in the RXRPC backend that allows you to do an in-place decryption on top of another page. Okay, we'll go into how this all works in a second. Now, what's interesting here is, you're probably thinking like, wait, doesn't the kernel assume that the user provided data could be malicious? Well, there's actually, generally that's the case, right? Generally, when you take input from the user and you're using these pages that the user provides, there are methods to prevent the user from being able to just provide arbitrary data. So the first one is, normally socket buffers are called copy on write. Like, so basically, this is the origin of the dirty cow bug, by the way. Copy on write is this way that the kernel allows you to be very performant with memory until you write to it, right? So let's say, for example, we have a buffer from the network or something, right? And like, it exists in the kernel at one location. If some other process or some other user uses this page, right, it may exist and be owned by somebody else, right? And we can technically read from this if we have read permissions on it, and that's fine. It'll use the same page. It only becomes a new copy when we write to it. We basically use this as like a local cache so that we don't have to make multiple copies for every use of it. We only copy it on write. And so because of this, right, if I had a normal page of memory, right, I had a block of memory with a bunch of data in it, if I were to try to do a decryption on that data, what would actually happen is internally it would make a new copy of the data in a new location so that the copy on write would not allow me to modify other parts of the scatter list, right? It would make a new page that would not be referenced by other cache hits, right? Now, this is where this gets really weird. In certain variants, I think unintentionally, of these crypto algorithms, they are done in place. So the bug for the ESP variant, the one that is not allowed on Ubuntu, in the ESP input check, basically, right, it's checking to see if it should do the copy on write or not. And if the socket buffer is nonlinear, meaning it has this fragment list, which could point to other pages, it skips cow, it skips copy on write. So because of this, we are using pages in memory as the source and destination to do decryption. And just like copy fail, what this allows us to do is do an arbitrary 4 write byte out of memory and use that to store 4 bytes of memory into a page that we don't necessarily control. So what happens here is very similar to copy.fail, right? We have these pages of memory, right? We do a splice operation, which points to user bin su, right? UBSU, we call this user bin su. And then so we do some kind of IPsec ESP operation on this. And while it's doing this in-memory decryption, it uses the end of the scatter list, which is now a scatter list. A fragment list and a scatter list are different structures, but there are functions that convert one to the other. And so it uses this crypto routine in place, because we're not doing copy on write, to effectively do a 4 byte write into user bin su. Very similar to copy fail. This is the first variant. Now, what I'm about to say is kind of crazy. This isn't even the cool one. This isn't even the crazy one of these two variants, okay? So this, again, is the ESP variant, right? This is the variant of the two vulnerabilities that uses the IPsec ESP write, that uses out of bounds memory as a scratch pad, and under the hood is going to overwrite a different frag, okay? This one uses an entirely different protocol, RXRPC. Again, I have no idea what this is, but under the hood, what is going on is super interesting with this bug. So using the same primitive, again, the same primitive where we take the list of pages, right, and we splice together one page with another and get access to a new file. So in the previous version, the ESP version, we're trying to overwrite the page cache entry for the contents of user bin su, so that when we exec ve user bin su, it just points to shellcode, all right? For this variant, the RPC variant, we're going to do something a little different. We're going to overwrite a text file. The reason for this is this variant is much more complicated. So what's actually going on in this variant is the RXRPC security is doing a version of crypto called fcrypt. Now, I don't know what fcrypt is in particular, but apparently it is a dedicated cipher, a block cipher, using the within the Andrew file system that has a 56-bit key and an 8-byte block. So it's a block cipher, okay? Now, what's happening here is in the subsystem in the kernel that runs RXRPC, it's doing these decryptions in place. You'll see here we take the socket buffer to making it a scatter list vector, right? A scatter list group vector. In the previous video, we talked about we had scatter lists. Again, think of like that frag list where page lengths and offsets. The scatter list is kind of the same thing, but not associated with a socket buffer. It's literally just taking the socket buffer frags and converting it to a scatter list group. You'll even see here, I think this comment is real. Decrypt the socket buffer in place. By the way, we probably want to decrypt this directly in a target buffer and not do it in place. And like they left that in there, which is honestly insane. But what makes this bug so crazy is the decryption is being done in place, okay? What does this mean? This means the decryption, the ciphertext and the plain text are the same buffer, okay? So they don't even get to decide the ciphertext for this bug. What they have to do is brute force the algorithm to choose a key such that the end state of the decryption is what they want it to be, right? And this is why they're overriding etc password and they're not overriding the user bin su, because they can't possibly reason about writing a 192-byte binary, which they do in the previous variant. Now, mind you, this is etc password. This is not etc shadow. In etc password, you have this X entry, which means, hey, yeah, there is a password for this user, but it's in a different file. The princess is not in this castle. Sorry, not sorry. So what they're doing, guys, is they are brute forcing the key to generate the plain text from the ciphertext, which is this, by the way, such that instead of generating an X, they generate nothing. They replace this part of the string with the rest of this. What this gets you is an empty field in etc password, which tells PAM Unix, by the way, root doesn't have a password anymore, sorry. So they in memory brute force the decryption, and then when they try to execute user bin su uses the page cache entry of etc password, which now has nothing for the root entry, okay? So again, if you want to read kind of like the total end-to-end how this works, way more complicated than my explanation, right? This would take me, I think, literally a 3-hour video to go in every detail. But what they do in the exploit primitive is they literally brute force over every byte, right? And then they use a loopback interface to create the session, which with the key they've now brute forced decrypts in place in memory the etc password file here to the same file, but they just shift the string over a little bit such that when they run user bin su, they get root with no password. Dude, whoever figured this out, like we gotta hire that guy. We gotta get them working somewhere cool. You know what I mean? Like, damn. Anyway, y'all, that's it for now. Appreciate it. Thanks for watching. Yeah, that's it. I'm so in shock at the quality and like how complicated these bugs are. But not only that, like the speed at which they're coming out. Like copy.fail came out, I think, literally last week, and now we're seeing two. Like, this is not one bug, guys. This is two different bugs, one of which is unpatched that came out a week after copy fail. I think this is kind of just the new paradigm with AI enabled vulnerability research, right? People that are already like kernel exploit primitive masters can now just search like such a higher velocity that it's honestly insane. Anyway, that's it guys. Thanks for watching. Hit this video, go check it out.